Digital logic design is the foundation of modern computing. It is the art of designing electronic circuits that process and manipulate information. At the heart of digital logic lies the concept of number systems. Number systems provide a way to represent numerical values using symbols or digits. In digital electronics, these symbols are represented by different voltage levels, typically high and low, corresponding to 1 and 0. Understanding number systems is crucial for anyone involved in digital logic design. It provides the language through which we communicate with digital circuits. We will explore the four most common number systems: binary, decimal, octal, and hexadecimal. By understanding these systems, we can build the digital devices that power our modern world. Binary is the most fundamental number system in digital electronics. It uses only two digits, 0 and 1. In digital circuits, bits are represented by high and low voltage levels. Transistors switch between on and off states, forming the basis of digital logic. Binary forms the foundation for data storage, processing, and transmission in computers. Decimal, the number system we use in our everyday lives, is a base 10 system. It uses 10 distinct digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Each position in a decimal number represents a power of 10. For example, the number 256 represents 2 times 10 to the power of 2, plus 5 times 10 to the power of 1, plus 6 times 10 to the power of 0. While decimal is intuitive for humans, it is not as directly compatible with digital circuits as binary. Converting between decimal and binary is a fundamental task in digital logic design. This conversion process involves dividing the decimal number by 2 repeatedly and recording the remainders, which form the binary representation. Despite its indirect relationship with digital circuits, decimal remains important in digital design. It is often used for user interfaces, input-output operations, and for representing values that are more easily understood by humans. For example, the number of files in a folder or the resolution of a screen is typically displayed in decimal. Octal is a base 8 number system that uses 8 digits, 0, 1, 2, 3, 4, 5, 6, and 7. It provides a more compact way to represent binary numbers, especially when dealing with large binary values. Each octal digit represents a group of 3 binary digits, bits. The conversion between octal and binary is straightforward. Each group of 3 bits in the binary number is converted to its equivalent octal digit. For example, the binary number 101100 can be grouped as 101100, which converts to the octal number 54. Octal was once widely used in early computing systems due to its close relationship with binary and its more human-readable format compared to long strings of ones and zeros. However, with the widespread adoption of hexadecimal, octal is now less commonly used in modern digital design. Despite its decline in popularity, octal still finds applications in some specialized areas of computing, such as file permissions in Unix-based systems. Understanding octal can be beneficial for those working with legacy systems or specific applications where it is still employed. Hexadecimal, often shortened to hex, is a base 16 number system. It uses 16 digits, 0 through 9 and A to F. The letters AF represent the decimal values 10 to 15 respectively. Hexadecimal is widely used in digital logic design as a shorthand notation for representing binary numbers. Each hexadecimal digit represents a group of 4 binary digits. This grouping makes it very convenient to convert between hexadecimal and binary. For example, the binary number 11010011 can be grouped as 11010011, which converts to the hexadecimal number D3. The use of hexadecimal greatly simplifies the representation and manipulation of large binary numbers. It is commonly used in assembly language programming, memory addressing, and data representation in computer systems. For example, colors in web design are often represented using hexadecimal codes, such as #FF0000 for red. Understanding hexadecimal is essential for anyone working with digital systems. It provides a more human-readable and manageable way to work with the binary data that forms the foundation of digital electronics. Converting between number systems is a fundamental skill in digital logic design. It allows us to translate numerical values between different representations. We've touched on binary to octal and hexadecimal conversions. Converting decimal involves more steps. Divide the decimal number by the base and record the remainders. Read remainders in reverse for the target system. Multiply each digit by its positional value and sum the results. Online tools help, but understanding principles is crucial. Mastering conversions is essential for interpreting memory addresses and more. Number systems are not just abstract concepts, they are deeply ingrained in the physical implementation of digital circuits. At the most basic level, digital circuits use voltage levels to represent binary digits. Typically, a high voltage level represents a binary 1, while a low voltage level represents a binary 0. Logic gates, the building blocks of digital circuits, operate on these voltage levels to perform logical operations. For example, an AND gate outputs a high voltage, 1, only if both of its inputs are high, 1. Otherwise, it outputs a low voltage, 0. These logic gates are interconnected to create more complex circuits that perform arithmetic, data storage, and control functions. The number of bits a digital circuit can process simultaneously is referred to as its word size. A larger word size allows for the representation of larger numbers and increased processing power. Modern computers typically have word sizes of 32 or 64 bits, enabling them to handle complex computations and large amounts of data. Arithmetic operations, such as addition and subtraction, are fundamental to digital logic design. In binary, these operations are performed using simple rules. Binary addition follows the same principles as decimal addition, but with a base of 2. When adding two binary digits, 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 10, where 10 represents 2 in decimal. The carryover mechanism is similar to decimal addition, where a carry is generated when the sum of two digits exceeds the base, 2 in this case. Binary subtraction follows similar rules. 0 minus 0 equals 0, 1 minus 0 equals 1, 1 minus 1 equals 0, and 0 minus 1 equals 1, with a borrow from the next higher bit. Borrowing in binary is analogous to borrowing in decimal subtraction. Digital circuits implement these addition and subtraction operations using combinations of logic gates. In addition to arithmetic operations, digital circuits also perform logical operations on binary numbers. Logical operations manipulate individual bits within a binary number based on logical conditions. The three fundamental logical operations are AND, OR, and NOT. The AND operation outputs a 1 only if both input bits are 1. The OR operation outputs a 1 if at least one input bit is 1. The NOT operation inverts the input bit, changing a 0 to 1 and a 1 to 0. These basic logical operations can be combined to create more complex logical functions. Logical operations are widely used in digital circuits for tasks such as data comparison, decision-making, and control flow. For example, a simple circuit could use an AND gate to check if two input signals are both high, triggering a specific action only when this condition is met. Number systems and digital logic design form the backbone of computer architecture. From the way data is stored in memory to the instructions executed by the processor, these concepts are intertwined at every level. Memory organization relies heavily on binary addressing. Each memory location is assigned a unique binary address, allowing the processor to access specific data. The word size of the processor dictates the amount of data that can be accessed in a single memory operation. Instruction sets, the language understood by processors, are encoded using binary codes. Each instruction, such as addition, subtraction, or data transfer, is represented by a unique binary pattern. The processor decodes these instructions and executes the corresponding operations. Understanding number systems and digital logic is crucial for comprehending how computers work at a fundamental level. It provides the foundation for designing, programming, and troubleshooting these complex systems. In conclusion, number systems are not merely theoretical concepts, but rather the language through which we communicate with and design digital circuits. From the binary digits that represent data to the logical operations that manipulate it, number systems are woven into the fabric of computing. For learners, a firm grasp of number systems is essential for understanding the principles of digital logic design. It provides the foundation upon which more complex concepts can be built. For professionals in the field, mastery of number systems is crucial for designing efficient circuits, writing optimized code, and troubleshooting complex systems. As technology advances and digital systems become even more integrated into our lives, the importance of understanding number systems will only continue to grow. By embracing these fundamental concepts, we equip ourselves with the tools to shape the digital world around us.